Okay, so moving on. I think I skipped ahead one here. Okay, so why is it important that we consider multi-compartmental models when the data doesn't really fit a one-compartment model? Like I said, we almost always use one-compartment models because, as you'll see, the calculations get pretty crazy with two-compartment or three-compartment or however many compartment models we need to describe the data. We almost always use one compartment. But the reason that sometimes we can't is if the data is oversimplified as a one compartment model, errors can be made because you can overdose people because volumes are incorrect. Because as we've talked already, you know that in some cases we need to use that first compartment or that central volume where the drug initially distributes rather than where the drug eventually will distribute at steady state, especially for loading dose. So if you're using a loading dose, you're going to want to use that first compartment, which sometimes is called the central volume. As in kinetics, one of the things that's difficult is we use different terms. But this usually corresponds to that first volume of that first compartment that we were talking about. So there's that central volume, which are drugs, or where the drug goes initially, which usually corresponds to our first volume. Then there's also what we call V zeta, which is the volume that's calculated using that final slope. And so when we talked about the natural log concentration time curve, if we've got this, we know we have more than one compartment, and based upon this, whatever the last slope is. Now, like I said, most of the time we're going to just have two compartments that we'll be talking about. But you could have, an infinite number of compartments. So V zeta just means that last slope. So if it's two compartments or if it's 25 compartments, it's whatever the last slope is. You have a volume that you can calculate using this last slope, and I'll show you that in just a minute. So this is also sometimes considered the apparent volume of distribution that we've talked about before. So it's a calculated volume. It doesn't necessarily represent physiologically what's happening, which is the difference between that and the volume of distribution at steady state, which is what we use from a physiologic standpoint to make decisions about what to do with dosing regimen. This is actually a physiologic volume, which is hard to measure because people object when you measure your plasma volume or your tissue volume and drain all your blood to measure it. People don't like it. Measuring your protein binding isn't that difficult, but measuring binding in tissues gets kind of invasive too. So it's hard to actually measure these. So usually we assume that calculated volume or apparent volume is approximately equal to our volume of distribution at steady state. So we use them kind of interchangeably. So what should we use when we're doing loading dose VC? What should we use when we're determining half-life? Remember, half-life and K are dependent upon clearance and volume. So what volume do we use here? Do we use V1, V2, something in between? Well, we use actually this calculated VZ. And again, we assume that it's approximately equal to that physiologic volume at steady state. So here's how you can measure all of those. So by using, as you can see, you can use your macro and micro constants here. These are all macro constants. Remember, your macro constants are your y-intercepts and your slopes of your different compartments. So you can get VC by, and you guys already know this, by your dose divided by your initial concentration. So if you have two compartments, you can measure, you can add up the two y-intercepts to get your total concentration at time 0, because remember those slopes, there's C1, C2, those added up will give you your actual concentration that you have at initial. Oh boy. And then V zeta, like I said, can be calculated from that final elimination slope by dose over K2. So again, it's that, shouldn't have erased that. So here's your slope, K2, C2, that's your y-intercept, and then here's maybe C1 and K1. So you can find your V zeta. Remember I told you it was going to be off of the slow slope here. Oops. So take your K2 there, and it's dose over K2 times the area of the curve, or clearance divided by K2, because this is clearance, isn't it? Dose over area of the curve is the same thing as clearance. So you determine your V zeta using that the slowest compartment slope here. Volume distribution at steady state can be calculated by using your central compartment, which you've calculated up here, plus these micro constants. Remember, the micro constants are, if you have compartment 1 here and compartment 2 here, drug is coming in here, it's moving from first compartment to the second compartment, so that's K1, 2, and back to the first compartment from the second is K2, 1. So once you figure those out, which I'll show you how to do in a little bit, you can determine VSS that way, or you can say dose over your C1 over K1 squared plus C2 over K2 squared over intercept over slope again for your first compartment, plus your y-intercept for your second compartment over your slope of your second compartment, that whole thing squared. So there's a couple ways you can figure out your volume of distribution at steady state, but the fact is that you can, once you have your micro and macro constants, you can determine all of these volumes. That's it for that.